Good morning students. This is our first video lecture of physics. I am Sujata, your physics teacher. Let us discuss today chapter 3, current electricity. As earlier we have seen, when the charges are at rest, the electricity produced is called static electricity. But when the charges are in motion or when the charges are flowing, they produces current and the electricity related to it is known as a current electricity. Consider a conductor and the Q charges are flowing in that conductor across a area A in an interval 0 to t, such that the charges flowing in the conductor is proportional to time t. This type of flow of charges is called steady flow, or we can say that the charges are having constant velocity. The steady current most of the time we see in domestic circuit, it is 2 ampere, 5 ampere, and variable current we will see most of the time in lightning. Steady currents in this chapter we are talking about this most of the time. Now let us discuss the next term, which is called electric current. As we have seen earlier, a steady electric current means where Q is proportional to T. Q, the charges which are flowing in interval of time T. Q proportional to T. What is the definition of current? Current, charges flowing per unit time or charges flowing in a unit time is called current. We can write the unit of current as 1 ampere equal to 1 coulomb upon 1 second, as coulomb is a unit of charge and second is a unit of time. But if the current is variable, how we will write the current? Current we can write in two terms. Either we will write current average. Current average means delta Q by delta T, which is equal to Q2 minus Q1 upon T2 minus T1. That means the total charges which are flowing in the interval from T1 to T2. Or we can talk about an instantaneous current. Instantaneous current I is a function of T, and here for that particular time T we can find limit delta T tends to 0 delta Q by delta T. Ampere. Ampere is a unit of current, but this is a very big unit. As we know, 1 ampere equal to 1 coulomb per 1 second. But what is coulomb? In 1 coulomb, we are having near about 6.25 into 10 to the power 18 electrons. 1 ampere is a big unit because we are having such a tremendous amount of electrons which are flowing in 1 ampere. Let us discuss the next topic, electric currents in conductor. As we know, in a conductor, we are having more free electrons inside a conductor. Inside a conductor, the electric field is 0. As we have seen in the earlier chapter, the electric field inside a conductor is 0. What will happen in absence of electric field? In absence of external electric field. Due to thermal energy, the electrons are moving here and there inside a conductor. When the electrons are moving randomly here and there inside a conductor, the total electric field in absence of external field, the total field will become 0. In presence of external electric field, the electron will experience a force and they get drifted. So how the electrons are drifted? Let us consider a conductor. Electric field we have applied to the conductor. Electric field is always from positive to negative. The electrons which are present inside a conductor, they will move in the opposite direction to the external electric field, such that the negative charges will be there at one side and positive will be there at another side due to deficiency of electrons. Then the external electric field and the internal electric field which is produced due to drifting of electrons, the sum will become equal to 0. So the current inside the conductor, when we apply external electric field, it will be there only for a small interval of time. But if we want the current continuously for a longer time, what we have to do, we will see in the next slide. Let us discuss the basic laws related to steady flow of currents. When a steady currents are flowing through a conductor and we need a mechanism for it. What mechanism we need? We have to maintain a steady electric field. We have to maintain steady electric field across a conductor. Always there should be the supply of plus Q and minus Q charges which can cancel out the charges which are produced inside a conductor, and thus this work is done by cell or battery and we will get a steady current. So if we want a steady current through a conductor, a mechanism which we use is either you connect a cell or a battery across a conductor, which will provide a fixed electric field and we will get a continuous electric current. A basic law which is there for the steady currents, it is called Ohm's law. What is Ohm's law? The potential difference across the two ends of a conductor is directly proportional to current flowing through it at constant temperature. V is proportional to I. Here I have taken a conductor of length L, its area is A and potential applied is V. V proportional to I, here we will get V equal to IR. What is R? R is a constant which is given by V by I. Its unit is ohm and it depends on length and area of cross section of the conductor. Let us see how the resistance depends on length and area of cross section of a conductor. Consider a conductor of length L and consider another conductor same with length L, same material, and both are having area of cross section A. We have applied a potential difference V across first conductor and potential difference V across second conductor. Current I is flowing through both the conductors as they are kept in series. The current is same. Now as we see R equal to V upon I. Here now the R dash will be 2V upon I. 2V upon I, it is equal to 2R. So R dash will become 2R. So as from this diagram you will see, as the length increases L to 2L, the resistance will become 2R. That means resistance is directly proportional to length. Increase the length, resistance will also increase. As we have seen earlier, R is proportional to L. Now let us see how R is dependent on area of a conductor. Take the same conductor of area A, length L. Area A and length L. Put a horizontal cut in such a way that the conductor is divided into area A by 2, A by 2. Potential V is applied across it. Current I is flowing through it. It gets divided I upon 2, I upon 2 for each conductor having cross-sectional area A by 2. Again we are having here I. Now what is R dash? R dash is the resistance for this conductor. R dash equal to V upon I by 2. I by 2 current of each conductor. It will become 2V upon I. 2V equal, that is 2R. When the area become half, the resistance, it becomes 2R. Resistance becomes 2R. That means area and resistance, they are inversely proportional to each other. One is decreasing and another is increasing. So we can write R inversely proportional to area of a conductor. Combining 1 and 2, we can write R proportional to L upon A. proportionality sign we are removing by constant which is known as resistivity. R equal to rho L upon A. Resistivity rho, it only depends on the material of the conductor, but it does not depend on its dimensions, that is length and area of cross section. Now, as we got the equation for R equal to rho L upon A, let us use it in Ohm's law. V equal to IR, V equal to I rho L upon A. I upon A is nothing but current density J. It is called current density J. Use this current density J, so our equation will become V equal to J rho L. J current density, rho resistivity, L length of the conductor. But in second chapter we have seen V equal to EL. Actually we have seen V equal to ED. At the place of D we have written L. So V equal to EL. Substitute here. EL equal to J rho L. L will cancel out from both the sides and we are getting a relation E equal to J rho. J current density, rho resistivity. Resistivity is a reciprocal of conductivity, that is sigma. Resistivity and conductivity, they are reciprocal of each other. So using earlier equation, at the place of rho, 1 by sigma, and you will get sigma E equal to J. Students, please note down this all in your notebook so that easily you can derive the next relation. So note down this, the relation between E and J, and we have to write a relation between J and conductivity. This formula J equal to sigma E, it is equivalent to the Ohm's formula which is given as V equal to IR. We are going to discuss about drift of electrons and origin of resistivity. Drift of electrons is there due to the external electric field. But what will happen in absence of external electric field? In absence of electric field, the electrons, due to thermal motion, they are moving randomly here and there, and after colliding with ions, again they emerge out with the same velocity. Due to their random motions, the total electric field will be zero, and the average, suppose we take a ith electron, then the Vi average will become equal to 0. Here n is the total number of electrons. In presence of electric field, as we have seen, the electrons get accelerated and force acts on the electrons. The force on the electron can be written as mass of electron and acceleration of the electron. F equal to m(a)e. AE represents the acceleration of electron. As we have seen in earlier chapter, F equal to QE. Q, charge of electron. So I can write F equal to EE. Combining these two equations, m(a)e equal to EE. But what is E? Charge of electron, it is negative. So acceleration of electron, or the electron which get accelerated due to the external electric field, is minus E upon m. Minus E upon m. Now the velocity in presence of external electric field, it will become Vt at time t minus E upon m into t. What is t here? It is a time between the successive collision of the electron with the ions. Drift velocity. Drift velocity is nothing but the final velocity average. V equal to U plus AT. V, Vt average, U initial, Vi average, AT, A minus E upon M into T average. T average relaxation time average. That means sometime the relaxation time of the electron is less and sometime it is greater. So we have taken an average and the relaxation time average, it is written as tau, or we can simply say tau is the relaxation time. So what is Vd? Vd, we are getting drift velocity of the electron in presence of external electric field. It is equal to minus E upon m into tau. M, mass of the electron, tau, relaxation time. This drift velocity, if you see very carefully, it is independent of time. This tau is the relaxation time. This tau is the relaxation time. Drift velocity, the relation is given as minus E upon m into tau. This relation we are using in the next slide to obtain the relation for resistivity. Students, now we are going to derive a relation between current density and the relaxation time, or a relation between conductivity and relaxation time, or you can say resistivity and relaxation time. This is a very important derivation of 3 marks. Most of the time it is asked in the board exam. For this derivation, let us start with a conductor. A conductor is taken and we are applying an external electric field. For this conductor, the direction of external electric field is from right to left. And as we know, the electrons, they will move in the opposite direction to the external electric field, that is from left to right. The reason I told you many times, the electric field direction is from positive to negative and the electrons will move towards the positive end, so it is opposite. I have taken a conductor of length delta x, and this delta x or distance delta x we can write as Vd delta t. Now you are knowing Vd. Vd is a drift velocity which is produced due to electrons in presence of external electric field. We have taken a conductor and the electrons are moving in time delta t with a velocity Vd. They will cover a distance Vd delta t. Distance is velocity into time. Delta x equal to Vd delta t. This delta x, the distance covered by the electrons in time delta t, Vd delta t in interval delta t. Let us suppose small n is the number density of electrons. What is the number density? Number density is total number of electrons divided by volume, and volume means area into distance, area into length. In this case, n, small n, total number of electrons divided by A, that is for area of this conductor, and Vd delta t, the distance covered by the electrons in time delta t. N, small n, A, Vd delta t, that is the total number of electrons which are flowing in interval delta t. In interval delta t. What is the total charge? Total charge we have studied in 10th class also. Q equal to total charge equal to number of electrons multiplied by charge of each electron. Total charge, that is number of electrons multiplied by charge of each electron. Q, total charge which is flowing in this conductor in time interval delta t is NaVd delta t. And what is the charge of each electron? Minus E. Here I have used Vd in modulus sign because as you know, the Vd for electron is minus E upon m into tau. Here I have written it in modulus sign. As electric field is from right to left and electrons are moving from left to right. But here we want to find out the charge in the direction of electric field. Charge which is flowing in the direction of electric field. But the charges and the electric field are opposite to each other. So we have to add a negative sign to the total charge. Minus, again minus of NaVd delta T into E, that is charge of each electron. As we know, Q charge is I delta T. I delta T. And what is Q? NaVd delta T E. I have cancelled out delta T from both the sides. I upon A N Vd into E. Now substitute the modulus or the positive value of drift velocity. E upon M into tau into E. I upon A, in earlier slide we have seen, it is a current density J. J equal to N E square E upon M into tau. This is the important relation between current density and the electric field and the relaxation time. Electric field relaxation time. J, as we know, J equal to sigma E. What is sigma? Conductivity. Sigma E N E square E upon M into tau. Cancel out E from both the sides. We are getting a relation between conductivity and relaxation time. Sigma equal to N E square upon M into tau. What is sigma? Sigma, and that means conductivity and resistivity, they are reciprocal of each other. Conductivity and resistivity, they are reciprocal of each other. So sigma is written as 1 upon rho. And what is 1 upon rho? Reciprocal of this, M upon N E square tau. What is tau? Relaxation time. So this relation between J and tau, relation between sigma and tau, relation between resistivity and tau, all these relations arises due to drift of electrons, and this drift of electron arises due to the presence of external electric field. So conductivity and resistivity arises when the electrons get drifted in presence of external electric field. Students, you have to write down this derivation. I hope you are listening to this video, watching this video with pen and paper in your hand. You have to write down this in the notebook. You have to complete your notebook. When reopening of the school will be there, we teachers are going to check your notebooks. So go through it. Write down in the notebook. Go through the chapter. If you are having doubts, you can ask your doubts. And now you try the next example 3.1 on your own. In that 3.1, we are using the relation I delta T equal to N A Vd delta T E. Just try at least the example 3.1, and you have to the habit to solve the numericals, not to hesitate in solving the numericals. Okay, bye then.